Nation.
Amazing. Okay.
Okay, all, welcome back to Glow. Unfortunately, we had no session in April, but now we're back. We're happy to have Chris here today on incorporating scale into GNNs. And later we will have Jonathan as well from Technion. Yes, we will have our usual format as always. So Chris will have a 15-minute talk, and then will Jonathan have his 15-minute talk. And we will defer all questions and discussions to the interactive discussion round afterwards in the breakout rooms. Cool. Thank you. And Chris, you can start.
All right, awesome. Thanks for having me. Yeah, I'm Chris. I'm at TU Munich, and I work with Bastian, Michael, and Daniel. And today, for the next 15 minutes, let's talk a bit about the notion of scale and how it interacts with graph neural networks. So, oh, wait. Yeah, there we go. I'm sure in this audience, I don't have to talk about the benefits of using GNNs, especially if we want to solve problems in science. What this talk is on is an area where GNNs don't work well, a failure mode. And this failure mode appears if we ask GNNs to generalize across scales. So what do we mean by this? To see this, let's have a look at an actual example, and let's take the QM7 dataset. If you're not familiar with this dataset, this is a graph level dataset. So we have multiple graphs, and what we're tasked with is predicting the atomization energy of molecules. So each graph corresponds to a molecule, and what we have to predict is how much energy we have to pump into the molecule to break up all of the chemical bonds. And because we want to apply graph learning methods to this task, obviously we represent each molecule as a graph. And doing this in a physical sense corresponds to fixing a resolution scale, because what we've settled on is talking about interactions of atoms. So in this abstraction, in this graph abstraction, each atom inside this molecule is being represented by a node, and then interactions between individual atoms, they're represented by the edges. From a physical perspective, nothing forces us to look at the system at this resolution scale. We could equally well talk about interactions of protons and neutrons inside the atomic cores, inside of each node, inside of each atom. Or at even higher resolution, we could talk about interacting quarks. Now, what here we want to do is have a look at how GNNs struggle with the notion of scale, and we're given a data set. So increasing the resolution scale beyond what is given, this is something we can't do. So instead, for the sake of our experiment, what we do is we lower the resolution scale, and we do this via coarse graining. So in going from the high resolution data on the left to the low resolution representation on the right, what we do is we take the light atoms, the hydrogen atoms inside our molecule, and we just lump them on top of the heavy atom to which they're bound. So in this ethane molecule example that we have here, we take the hydrogen atoms and we just pretend they now sit at the position of the carbon atom. And so now we have two graphs representing the same underlying structure, and we have this for each graph in the data set. And then what we can do is we can ask a simple question like, okay, what happens if we, for example, train our network completely on the high resolution graphs, and then we do inference on high and low resolution? So this is what we've done here for, the most simple graph neural network, the GCN network. And what we find is the error that we make in predicting, the unit here is kilocalories per mole, doesn't really matter, smaller numbers are better. What we see is we get a reasonable error, quite good. But if we train on high resolution data and then do inference on a different resolution, we do inference on low resolution data, the error that we make nearly doubles. So we are a lot worse in predicting what the molecular property of this atom, of this atomic graph, of this molecular graph is. And this persists for essentially all of the models. And what we can see is the more complex the model gets, for example, this one here, PushNet, which tries to have like a multi-scale propagation scheme inside the layers, we see that, well, we start sort of with the same error if we're training on the same resolution that we do inference on. But then if we do inference on a different resolution, the error goes completely haywire. And this is also true in the opposite direction, where we train on low resolution and we now want to do inference on high resolution. So we don't have generalization across scale, which, this is a failure mode. What is the underlying problem? Why doesn't this work? As it turns out, the underlying problem is that our graph neural networks, they're not continuous. Now, that's a bit of a strong statement, so we should make sure that we know what we mean when we say this. To see what's going on, let's look again at these two graphs that we had. The original graph where we have the heavy atoms and the light hydrogen atoms fully resolved, and the coarse-grained version where we have taken the hydrogen atoms and we've lumped them on top of the heavy atoms. What we can do is we can think of those two graphs as the initial and the final stage of a continuous graph deformation process, where we literally take the hydrogen atoms and we move them out of their equilibrium positions towards the heavy atom. And then in the final time step, at the final time, they have actually arrived on top of these heavy atoms. And so we have this continuous process where the graph on the left more and more approximates the graph on the right. And now if our graph neural networks, if they were continuous, what we would hope for is that if we have convergence in the input, we have something that more and more approximates something else, we would see this behavior also for the output, for the generated latent embeddings. So we would hope that because this graph more and more approximates the graph on the right side here, the latent embedding that we generate here also more and more approximates the latent embedding that we do generate for the limit object. And so this is something that we can check. We can generate the latent embeddings from a fully trained network for these deformed graphs and for the final graph. And then we can check the latent distance. And what we see if we do this is that we definitely do not have convergence. So for some methods, this error stays, of order 1. For others, the latent distance really goes, very, very, very far, very, very big. So these latent embeddings go very, very distant from each other. And so we don't have latent convergence. And that means we have no continuity, right? We have convergence in the input, no convergence in the output. And that's the definition of something being discontinuous. So now we've understood what is going wrong. Let's try to understand why it is going wrong. As it turns out, the underlying reason why this fails, why we do not have continuity, is that the propagation schemes that we have on the modified graph and the final coarse-grained graphs, these propagation schemes are very different from each other. Let's have a look. Let's have a look under the hood of our graph neural network. Our GNN, this is just, a stack of GNN layers and then a final aggregation. We don't really care about the aggregation that much. What we do care about are the individual GNN layers. And for the sake of brevity in this talk, let's look at the simplest GNN layer. Let's look at what's happening for GCN. If you do want to talk about what's happening for other, for other architecture choices, I'm very happy to talk about that later, or have a look at the accompanying paper. So, what does the GCN layer take as input? Well, obviously the node feature matrix. And then what does it do with the node feature matrix? It updates it. How does it update it? Well, it multiplies from the right-hand side the channel mixing matrix. We don't really care about channel mixing. What we do care about is how information is being moved over the graph. And this is done by multiplying from the left with the renormalized adjacency matrix. Normalized adjacency matrix, I'm sure you're all familiar with this, but let's just briefly revisit this. How does the entry for an edge in the renormalized adjacency matrix appear? Well, we take the original entry that we have in the actual adjacency matrix of the graph, and we essentially divide it by the square root of the degrees of the nodes that this edge connects. Now, in the QM7 dataset, edge weights, they correspond to Coulomb energies between two atoms. So the edge between two atoms gets associated an edge weight, and this edge weight tells us the energy that one of the atoms has in the electric field of the other. If you don't have a physics background, don't worry about this at all. What I'm telling you is that the edge weight scales inversely with distance. And now let's have a look at what happens for this renormalized entry for this bridge edge between these two clusters here as we move these hydrogen atoms towards the heavy atoms. This distance here, nothing changes because we don't move around the heavy atoms here. So this entry of the original adjacency matrix, this stays the same. But what does change are the degrees of these two nodes, right? Because degree, this is just sum over all of the incident edge weights. And here, well, we move this atom, for example, closer to this atom here. So we decrease the distance, it tends to 0. So 1 over the distance tends to infinity, meaning that also this degree here tends to infinity. And so when calculating the renormalized weight here, what we do is we divide something that stays finite, the original weight that we have in the adjacency matrix, by something that tends to infinity. So we effectively get that this entry tends to 0. We effectively do not have communication between left and right. And that's, of course, very different from the setting on the graph on the right-hand side, because here, definitely, we do have communication between the node on the left, representing this cluster, and the node on the right, representing this cluster. And because we have this increasingly disconnected effective propagation scheme here, that explains why we also have more and more different latent embeddings for this graph that we generate here through this GNN when we compare it with this graph on the right-hand side, right? Because the way that information flows over this graph is more and more different from the way it flows over this graph, just because we don't have any communication between these two clusters. And then that explains why we don't have convergence of the latent embeddings, and explains why our GNNs are not continuous. Okay, so we've understood the problem. Now let's solve it. What can we do about it? Well, we want to somehow connect the propagation schemes of the graph on the left-hand side and the graph on the right-hand side. What we've seen is that we can't do this using GCN, because if we use this renormalized adjacency matrix, we get this disconnected limit propagation scheme. And now the idea is, well, let's change the way that we move information across this graph here. And let's change it in such a way that we do have a connection to the graph on the right-hand side. And the way that we want to do this is that instead of using this renormalized adjacency matrix, we use this matrix here as the matrix implementing the information flow. So this is the matrix exponential of the negative graph Laplacian scaled to some time t. Now, this looks a bit weird. Why do we do this? Why should we choose this as our propagation matrix? What does that have to do with anything? Well, this matrix exponential has everything to do with the way that heat would move over this graph. So we can think of this graph as an assortment of coupled heat reservoirs. So each node corresponds to a heat reservoir, something that can store heat. And then edges correspond to bridges across which heat can flow. And then if we have an initial temperature distribution over the graph, x naught, and we want to know the temperature distribution at time t, we just multiply with this matrix here, this matrix exponential, also called the heat kernel. We multiply the initial temperature distribution with this heat kernel, and that gives us temperature at time t. Okay, great, but how does that help us? Well, we do have these edge weights that are very, very large. And in this heat setting, large edge weights correspond to large heat conductivities, meaning heat can flow very easily from one node to another. So if initially we have a different temperature here than we have here, and then we let time run, because heat can flow so easily, we're going to have an immediate equalization of the temperature across these this bridge edge with this very large heat conductivity, this very large edge weight. And so all of these nodes are going to have essentially the same temperature. And then on a larger time scale, then we're going to have temperature flow or heat flow between the part of the graph on the right-hand side and the subgraph on the left-hand side. And this is essentially what we have here as well, right? So here, if we have essentially all of these nodes have the same information stored, that's the same as just representing it via a single node. Same story on the left-hand side here. We can just represent it via a single node, and then we have communication between these two supernodes. And we actually make this precise in the paper, and what we prove is that as these red weights grow larger and larger, running heat flow here, so multiplying with this matrix, is more and more the same as projecting to this coarse-grained graph, running heat propagation here, and then interpolating back to the original graph. And so that means if we do implement information flow in such a way, we do have a connection between these two propagation schemes. And that should have solved our problem because, well, then the latent embeddings that we're generating, they should have something to do with each other. And the one generated for the graph on the left should converge to the graph on the right. This is actually true, and we can show that this is true. We have an experiment in the paper. For the sake of brevity, we'll skip this, and we'll actually just very briefly, because I know I'm running out of time, we'll very briefly talk about the architectures that we can build with it and verify that it actually has solved the problem. What we've said is if we do implement information flow in such a way with the heat kernel, then we do have a connection between propagation on the left and propagation on the right. Now, just using the single heat kernel, the single heat flow matrix is a bit boring. We can also use a weighted sum over heat flows that have progressed to various times. And what the theory tells us that we've developed is that you still have a connection between propagation on the left and propagation on the right. You can go even one step fancier. You can say, okay, it doesn't have to be a discrete sum. It can also be a weighted continuous sum of heat flows that have progressed to various times that gives us our propagation matrix. And also then will we have communication between the heat flow and between the information propagation on the left and on the right. And so that should have given us a continuous network, meaning that if we plug into our continuous network similar graphs, we should get similar latent embeddings. And if we do get similar latent embeddings for similar graphs, well, we could rerun our initial experiment of the coarse and the fine graph representations, and hopefully we would have generalization across scale. And we test this exactly in the same setup that we had before for two example matrices. So two examples of matrices that do arise in such a way. The exponential we've already talked about. If you do have an applied math background, maybe you're familiar with the resolvent. If not, take my word for it that this matrix here arises in such a way as heat flows that have progressed to various times, a continuous sum over such heat flows. And then we use these as the propagation matrices in our architecture. We redo our initial experiment. And what we see is we actually do have generalization across scale. We can train, for example, on high resolution, do inference on low resolution, and it's going to give us essentially the same error as doing training on high and inference on high. And I do believe that's my time, so I'm gonna stop here. Thanks for listening.
Thank you, Chris, very much for your nice talk.
Sure.
We'll defer the questions as always to the breakout rooms. And Jonathan, feel free to share your screen.